Okay, so in the last lesson we talked about area between curves. Now we're going to move on to the next part. And it's going to be about the volume of cross sections. So just to help you review, the area between two curves is dependent on which way you're integrating. Okay, so for the first one, A1, let's say this, we're doing this with respect to x, and this one with respect to y. Okay, I like to notate my functions like the top function is always f, the bottom function is always g. So in this diagram, function f is on top and g is at the bottom, so the area between this curve using the x-axis between my x, my partitions are perpendicular to the x-axis, in that case you integrate with respect to x, is going to be the top function, g, minus f minus g. And my a and b are bounds between a and b. In that case, just think if you remember it like that. Now, a of y, the area between the two curves in terms of y, that means my representative rectangles are horizontal, okay, because we're going from y equals 0 all the way to something bigger, so whatever that point b is. In that case, oh yeah, I should rewrite that. So this here should be C and D. Okay, so that means f of y is on top. Again, turn your head 90 degrees, see which one's on top. This one's on top. So f of y minus g of y. Okay, so in that case, from C to D, f of y minus f of g. So in that case, this one minus this one. And you integrate in respect to y, and then just go ahead and integrate that and evaluate it. Okay, so the assumption I'm going with f and g is that f is a function that's greater than g. So it's always on top. Okay, so it doesn't matter if it's g in terms of x or y. It doesn't matter. Okay, just always the case. That's how I like to do it. Okay. So in today's lesson, we'll talk about volume between cross sections. Okay. So remember, cross sections is, let's say, if I want to cut this battery in half, I have rectangles. Okay. If I cut this circle or this cylinder, I cut it in this direction, I have a circle. So when we talk about the volume of cross sections, the way you want to think about it is point, line, area, volume. So in that case, a point becomes line if you draw it connected, and if you integrate line, the next thing, this is 1 dimension, this is 2 dimension, and this is 3 dimensions. Think about my unit analysis. Unit squared, and units cubed. So what that essentially means is, if I integrate area between my bounds, I get volume. Okay, you can do this in terms of x or in terms of y. Okay. So the assumed knowledge that you must have for area between the volume of cross sections is you have to know how to do the area between curves. You have to know how to differentiate between the top function and the bottom function. Okay. The other thing is you have to know the basic area formulas. Okay, it's like square is base squared, rectangle is base times height, and triangle is like base times height divided by 2, and so on and so forth. So, a visual demonstration of what this is really about. Okay. Supposedly, I have a function, this is my f, and this is my g. Okay. If I'm integrating with respect to x, okay, my cross-section is I'm integrating with respect to x, that means my partitions are always going to be vertical. Okay. So what that means is, f of x is the one on top, one is g. Okay, so if you integrate that if you have the area formula, it comes out like this. It's like circles coming out, semicircles coming out this way. So in this case, this demonstration would be like this. Okay, this is my function. And if you do the look from the side, you have something that looks like this. So in that case, you have the width in this case, well in this case, the base width will determine the height, in this case, the height in this direction. Okay, but it's always the case except rectangles, because the rectangles must have a different, well, if you set it as a certain height, then it's always going to be the same height. Okay, so that's this diagram. Now, if I am wanting to integrate this function between, well, f and g, and I'll set my bounds between this and this. This is my base width. Okay, I'm integrating between c and d. That means my diagram would look something like, this is my function. I'm integrating in terms of from this all the way up over here. So if you look at the side, okay, let's think about the top and bottom function. You have this. Okay, so this is my top function minus my bottom function. Okay, so think of it like this. Same thing with y, but x, but in that case you look at this way. So in that case, the width will determine how high my function, my shape is going to look like. So if you look from the other side, you look something like that. So in that case, it connects further down. And again, this is just a random artwork I just did before class. Okay, in that case, my partition is horizontal. That just means I have a diagram that looks like this. Okay, see the difference between these two? Okay, what do you think the area, are the areas going to be the same? What do you guys think? Okay, well, I'm going to tell you right now, off the bat, the area, if you come up, the volume you come up with these shapes will be very different. Okay, so when they specify a certain way, you must do that certain way. You can't switch it. Okay, just remember that. Okay, so the height, in this case, as I mentioned, the height of this cross-section is determined based on the base width. Okay, this is my base, okay, between the two functions. In that case, okay, this diagram, this example here is not very nice because it's bounded over here. Anyways, so to talk about this, does the direction matter? Yes, it does. Like I mentioned, the volumes are very, very different. Okay, so the complete different shape, because the shape looks like this versus like this, you get complete different things. So just make sure the question says, in terms of x, you do it in terms of x. If in terms of y, then you must do it in terms of y. There's no way out. You just have to do it like that. Okay, so let's talk about the common area formulas. Okay, so let's go ahead with this. Okay, so square, area of a square is the base squared. So think of it like this. Base times base is base squared. Okay, so in that case, the rectangle area is equal to base times height, because my diagram looks something like this. Base times height. Now, equilateral triangle. Okay, 60, 60, 60. We have this diagram. This is my base, this is my base. So you have to find what the height is. Okay, so that means this part here is going to be, in this case, again, this is going to be half of b. And using Pythagoras' theorem, we know this part here is root 3 over 2b. Okay? So the area in this case is going to be base times height. So in that case, root 3 over 2 times b squared and multiplied by 2. Because area is base times height divided by 2. So in that case, my area here would be my height, root 3 over 2, times my base, times divided by 2. That's all you get. So in that case, it's going to be root 3 over 4 base squared. Okay. Isosceles triangle, there's two types. Okay, my isosceles triangle is my leg is equal of the same distance. In that case, you're going to end up with base times height divided by 2. So in that case, the area is base squared divided by 2, because base times base divided by 2 would be the area of this isosceles triangle. Now, if, on the other hand, you have a 90-degree angle, okay, that's poorly drawn, but in this case, I have my base here, and my base is my hypotenuse of this equilateral, this isosceles triangle. That just means, again, let's cut this in half. This is half of 2b. And this part here, because they're equilateral triangle, these must be the same length. In that case, my height is also equal to base, half of base squared. Okay? And that's what you get. So in that case, my area here is equal to base squared divided by 4. Okay? Okay, that's what you get. Base is equal, area is equal to base squared divided by 4. Okay, semicircle. My semicircle looks like this. Okay, this whole thing's my base. So in that case, my area is equal to pi r squared divided by 2. In that case, my radius is going to be half of base. In that case, pi times base divided by 2 squared divided by 2, which is equal to pi over 8 base squared. Okay. So in essence, you're just going to apply formulas, okay? And the base is determined based on the function that you choose, okay? So the base is going to be the top function minus the bottom function, okay? Well, let me add that right in. So that means essentially what this is going to be f minus g squared. This is going to be my height times f minus g, and this one's going to equal root 3 over 4 f minus g squared. And this one, isosceles triangle, would be f minus g squared divided by 2. And then isosceles triangle with the hypotenuse being the base is equal to f minus g squared divided by 4. And for the semicircle, it's going to be pi over 8 times f minus g squared. Okay, so just remember that. Again, f is always on top of g. Okay, just think of it like that. Okay, so my formula in this case, as I mentioned down here, I'm integrating with respect to x. It's just going to be from a to b of my function of my area of x, dx. And then it's going to be from c to d of a of y, dy. Okay? If you integrate with respect to y, you must do it in terms of y. X, in that case, do it in terms of x. Okay, so here are some intermediate steps for you to consider. Okay, first of all, sketch a function that's given to you and find the points of intersection. In that case, the points of intersection, in terms of x, find the x bounds. In terms of y, find the y bounds. Okay, rewrite if necessary. By that, I mean, if you're given in terms of y, you need to do it in terms of x, and just switch it. Just make sure you do it algebraically correctly. Just be careful. Okay, number 2, draw the direction of the rectangles. Okay, if I'm integrating with respect to x, my partition is going to be it's going to be vertical. Okay, let's go from the left to the right. Now, if you're doing in terms of y, your representative rectangle is going to be horizontal, going from the bottom all the way up. So that means that's kind of how you want to do it. Okay, just kind of like think about how this works and how that connects. Okay. Number 3, draw the cross section. Yes, these are the cross sections I'm talking about, and then label f and g. Again, f is on top of g. Okay, so here's a triangle for you to consider. This is an isosceles triangle. This. So what I'd like you guys to think about is if you have a cross section, the top is always on the right. So in that case, call that f, and the bottom g. Okay, and just remember that this whole thing here, this width between f and g, that's my base. Okay, if you draw this diagram up, you can use it to help you find the area formula. Okay, so in that case, for this rectangle, for this isosceles triangle, the area is base times height divided by 2. My base and my height are the same thing, so it's going to be base squared divided by 2. So for this example, the area for this one is A is equal to f minus g squared divided by 2. Okay, so that's that. Now, so last but not least is write the integral of the function and integrate. Do not forget your units. So in that case, it's just going to be the integral. So write it up in like this. So whatever you think you use in here, plug it in here. Just be sure that you're integrating with the right variable, x or y. Okay, so that's it for this part. In the next video, I'll walk through some examples for you to consider, and then I can derive this later. Okay, see you in the next one.